So if we're looking at a reaction, we can maybe propose a mechanism that is like the one we were looking at, where we have an intermediate formed. But the question is, can we tell this apart from just a single step mechanism, where A just directly goes to product with some rate constant K, K1, we'll call it. So this would be a single step mechanism, right, where we don't have any intermediate this form. And can we differentiate this based on observations of concentrations over time from the mechanism where we have an intermediate formed? Okay, so well, let's think about if we have this. We know that the rate, which is dA dt, will look exactly the same in terms of A. K1 times concentration of A. That means that our behavior of A, concentration of A as a function of time, is identical. Right, so this doesn't change. So even though we have a different mechanism, the behavior of our reactant concentration stays the same in this single step mechanism. What would change instead is our concentration of P, because dP dt is going to look different, right? We're going to have a positive K1 times A. So this will have a simpler expression. We can basically say, okay, well, P is equal to A naught minus A, and then we can plug in this part here in for A, and so we'll get A naught times 1 minus e to the minus K1t. All right, that just comes from plugging this in. We factor out the A naught, and we'll get this expression here. Okay, and so this, obviously, this expression here, I'll underline in red, this looks very different than this expression. Not that one there. Yeah, no, this is the product expression right here. Right, so we can see there is a difference here. But the question is, could we actually tell this apart if we were measuring? And there's sort of two cases that we can consider. There's more than just these two cases, but these are sort of the extremes. So we can imagine, well, what if the second step of our single step or of our two-step mechanism is much faster than the first step? And we can consider the other way around. What if K1 is much bigger than K2? What if the first step is the fast step? How does P behave under these conditions? All right, so coming back to our two-step mechanism, what is that equation is we have P is equal to A naught times 1 plus 1 over K1 minus K2 times K2 e to the minus K1t minus K1 e to the minus K2t. Okay, so let's look at first this case here. K2 is much faster. K2 is much larger than K1. Okay, so if K2 is really big compared to K1, when we compare these exponential terms here, this second term where K2 is here is going to get very small very fast. Goes to 0 very quickly compared to the other term here, right? Compared to this term here. So this term, this first term, will be much bigger than the second term, and so we can sort of approximate that this second term goes to 0 because of that very large value of K2. So that's sort of our definition here. We can also say here in this fraction, this denominator here, if K2 is much bigger than K1, we can sort of ignore the K1. It's not going to make a big difference. And so we can say, okay, assuming K2 is much bigger than K1, A naught, we'll have A naught times 1 plus 1 over negative K2, because again, K2 is much bigger than K1, so we can sort of ignore the K1 in the denominator there. And we're ignoring that second term, so we'll have K2 times e to the minus K1t. Let's draw a nicer bracket there. And that gives us that we have A naught times 1 minus e to the minus K1t. And so we can see this is identical to the single step. And so if K2 is much bigger than single step mechanism, if K2 is much bigger than K1, we can't even tell that there's an intermediate being formed because the intermediate is reacting so quickly, and our rate limiting step is the first step. And so because that's what we're saying with K2 much bigger than K1, this is with step 1 is rate limiting or rate determining. That means that we can't distinguish the behavior of a two-step mechanism from just a single step occurring. But let's consider the other case, right? So this one that I have here, where K1 is much, much bigger than K2. So we can go back to this equation here, and I'm going to rewrite it so I have space here. So again, our products will be equal to A naught times 1 plus K1 minus plus 1 over K1 minus K2 times K2 e to the minus K1t minus K1 e to the minus K2t. Again, draw a better bracket. There we go. Okay, so if K2 is much smaller than K1, or K1 is much larger than K2, either way you want to think of it, we're going to have the opposite case of everything that we decided before. So we'll have this, this term here is going to be our term that goes to 0. Same argument, right, that this term is going to sort of disappear. And again, in this denominator here, we're going to ignore K2. K2, because K2 is the K2 is the slow step now. Right, K1 is the fast step. Okay, and so we can go ahead and reduce this down. So we'll have 1 plus 1 over K1 times negative K1 e to the minus K2t. Okay, now our K1s cancel. So we'll get 1 minus e to the minus K2t. And now we see this is different, and the key difference here being that our K value in the exponent here is now significantly different, right? We have K2 instead of K1. So now we can distinguish from the single step, because the behavior of our product and the behavior of our reactant are going to be different because they're governed by different rate laws. And we can actually observe that if the second step is the rate determining step. So that's what's happening this one. Second step is rate limiting. All right, and so now we can actually distinguish these two processes. So in the next video, we're going to continue on with this same mechanism and look at an approximation that we can make to simplify some of the mathematics of analyzing reaction mechanisms, called the steady state approximation.